Alright, this is a standard equilibrium problem, except there's a nasty and subtle trick to it. You're given amounts of two reactants, initial amounts, and atmospheres, and yet here's Kc. So the very first thing that needs to be done is to convert Kc to Kp. And this is how we're going to do that. Kp equals Kc times RT to the delta N gas power. And delta N gas is the number of moles of gas in the products, which is 1, minus the moles of gas in our reactants, which here is 2. So delta N gas is minus 1. So that leads to Kp equaling Kc to the minus 1 power, or Kc divided by RT. So here we've done the math. We've converted K sub C to K sub P. Now again, this was just nasty, primarily because it was so subtle and easy to overlook. From here, we'll continue as a regular equilibrium problem. So we can do an ice table, initial, change, equilibrium, and our amounts will be given in atmospheres. So initially we have 0.21 of each of our reactants. We don't have any of our product. We lose X, and gain X. So the equilibrium, as always, is the initial plus the change. And we can plug in to our equilibrium constant expression. So K sub P is a pressure of POCl2 divided by the pressure of CO multiplied by the pressure of Cl2. Now we plug in the values from our equilibrium constant expression. We have X, 0.21 minus X squared. Multiplying out these terms in the bottom is going to lead to a binomial and a solution by the quadratic equation, unless we can use the approximation. So let's test to see if we can use a simplifying approximation. Now in the simplifying approximation, we multiply K by 1,000 and compare that product to this initial concentration, the concentration from which X is going to be subtracted. So 101.6 is definitely larger than 0.21, so our approximation is not okay. To solve for X, we first have to multiply out this binomial. Okay, to obtain this binomial, we use FOIL, multiplying the first terms together, the outer and inner terms together, sum to this, and then the last terms end up being X squared. Okay, we want to continue on, so we're going to use the strategy here of cross-multiplying. So this number times the denominator is going to be equal to 1 multiplied by X. Next, we're going to use a distributive property to multiply all of the terms inside the parentheses by this value out front. Alright, so the next step is to put this in the quadratic form so we can know that what A, B, and C are equal to. To do that, we'll subtract X from each side. Alright, so now we have our values of A, B, and C. Alright, so we've obtained our two roots. Typically, I just go online and use a quadratic formula calculator once I have A, B, and C. So we have our two roots. One is going to be the nonsense root, and one's going to make sense. We can determine which is which by looking up at our ice table. In our ice table, we can get our pressures of our initial reactants as 0.21 minus X. 0.21 minus 10 is going to lead to a negative pressure, and therefore that is the nonsense root, and the other is a true root. Okay, a quick summary. We first made sure we had the right value of k, so we could write our equilibrium constant expression, fill that in from values of the ICE table, solve for x. Now that we have x, we can go back and answer the question. All right, and finally here we are. We're looking for the equilibrium partial pressures. Now that we have our value of x, we can go back and plug that in, and we're done.